Thank you, and thank you for inviting me and for hosting this nice event. So I'm going to speak about a new joint work with Yuval Ishai, or Karni, my student, and Arpita Patra. So please feel free to ask questions. I haven't given a talk about this subject before, so this is like a world premiere. So please be patient if something is not clear at the first minute. The title is a bit lengthy, but essentially the talk is about much more basic question. We're going to talk about secure computation, and we're going to study kind of trade-offs between privacy and the level of interaction that is being needed. This is a very basic subject, arguably also fundamental and important. Good. So a quick introduction to secure multi-party computation. So we have n parties, and each party holds an input. It can be an integer or maybe a vector of many elements over some finite field or bit string. And the goal is to jointly compute some function over these inputs. So for example, if we think about integers, maybe we want to compute the average. And you can see that I wrote it like in the output also a vector of output. So in general, we can think about this function as delivering different values to different parties. Okay, so for example, maybe the first party should learn the average, and the second party should learn the median, and so on and so forth. Okay, so this is the general setting. And of course, we want some level of privacy. Right, so intuitively, the party should learn their outputs, but nothing else. And there are ways to formally capture it. Specifically, we want to get a protocol, right? So the party should talk to each other. At the end, they should learn the output of the function, so each party should learn each part of the output. And this notion of privacy is going to be quantified by parameter T. So we want T privacy, which means that every coalition of T parties learn nothing beyond their outputs. So for example, if we look at these two parties, so during the protocol, they see all sorts of values. They see the random tapes, they see their incoming messages, and so on. So we can think about it as a list of random variables. And we want to be able to simulate these random variables solely based on their inputs and outputs. Just a second. Okay. Good. So given this, the inputs x4 and its output y4, and the input x5 and the output of y5, we should be able to simulate, to perfectly generate a distribution of this view. Right? If you're familiar with zero-knowledge proofs, right, this is a very similar notion of simulation like we have in zero-knowledge proofs. Good. Now, in general, we distinguish between two basic settings, right? A passive versus active setting. So think about, so I talked about coalitions, but an equivalent way to think about this setting is to think about an adversary that corrupts these two parties. Okay, so there is some central entity, an adversary, that controls both the fourth and the fifth party, the green and the pink party. We can think about the case where this adversary is passive, namely follows the protocol, right, as prescribed, and in the end it tries to infer information, or the case where the adversary is active and deviates from the protocol. Okay, this is much more complicated setting, and one has to adapt the definitions accordingly, but for today I'm mostly going to talk about the passive setting. Okay, so by default, unless I say otherwise, we're going to think about the passive adversaries that follow the protocol as they are, as it is, what's also known as a semi-honest security. Good. And we're going to work in the information-theoretic model. That is, privacy should hold even if the adversary is computationally unbounded. Even if the adversary can compute everything, you should not be able to violate the privacy. You should be able to simulate the view of the adversary perfectly. Right? It's not with respect to computationally bounded parties. And this is somewhat similar to what Andre mentioned about statistical zero knowledge, right? When you want statistical indistinguishability between distributions. So there are several reasons to be interested in this variant. First of all, you get unconditional results. You don't have to assume anything, any hardness assumption. You don't have to assume that factoring is hard, and therefore you're less sensitive to the case where the adversary is a polynomial time machine or a quantum machine, etc. You don't even have to assume that P is not equal to NP, right? You have no computational assumption at all. Typically, you get for free strong composability properties, and which is nice, and it's not always the case when you work with computational security. Also, these kind of protocols tend to be concretely efficient even for small input sizes. Like when you think about like finite functions or smaller inputs, short strings. And somewhat surprisingly, maybe, even if you don't care about all these features and want to design computationally secure MPC protocols, it turns out that it's very useful to have information-theoretic MPC as a tool for designing computational cryptography protocols. And indeed, I think that it is safe to say that all the best, in terms of efficiency and performance, all the best constructions, even the computational ones, are typically based on this information-theoretic MPC, plus some tiny amount of computational crypto. And this in particular leads to, say, black box use of this cryptographic primitives of pseudo-random generators and so on, which is important both from a theoretical point of view and also for performance. When you make a non-black box use, typically you get things that are impractical. Almost finally, and very importantly, this setting is very simple. The definitions are very simple. The analysis is very simple. It's easier to teach these kind of things and also to study, right, to do research when you work with information-theoretic tools and primitives. And it really cleans many of the noise that we get in the computational setting, which kind of forces us to work in an asymptotic setting and talk about infinite sequences of things. And this brings it to the last point, which is very relevant to this current topic or current talk. It really allows us to focus on the core questions. Okay, and let me mention that many of them are still open. You will see some of them in this talk. And you can study them in the simplest, crystal clear setting, right? So, and in particular, you can restrict your attention to finite functions of constant size. So think about the constant number of parties, constant number of inputs. Don't worry about complexity. And it turns out that once you solve these things for finite cases, there are general ways to lift them up to more complicated things, to say to NC1 or even to the class P if you're willing to use black box pseudo-random generators in your protocol. So for this talk, I'm going to really focus on this finite world and forget about computational complexity. And again, this is kind of justified by these results. Good. Let me mention that even in this world, there are two variants. You can hope for perfect security, which means that, you know, error-free, right? The protocol never makes errors, and also the simulation is kind of perfect. You get things which are identically distributed, versus statistical case where you have tiny amount of error and maybe some privacy leakage. And typically in the passive setting, the protocols that we have are perfect, and indeed I'm going to kind of restrict this talk almost, it's going to be restricted almost for all the talk from this perfect setting. And when I move to the statistical setting, I will mention it and talk about it. So by default, we are in the perfect, simplest version of the protocols, perfect passive security. Good. So questions so far? Okay, so that was kind of a rough introduction to MPC. And in the literature, there are two main models, the plain model and the OT hybrid model. And I'm going to talk about each one of them separately, but let me kind of give you a spoiler. We're going to talk about a new model or recently a recent model, this multi-party randomized encoding, which is kind of in between these two models, and will show that answering questions in this domain will give us interesting answers to questions in both classical domains. Okay, so this is kind of a high-level plan of what we're going to do. So let's start with the plain model. So in the plain model, the parties are connected to each other by point-to-point private channels. Okay, and the protocol proceeds in rounds. So at the beginning, each party gets its input. This can be a vector of values, right? x1, x2, x3, x4. Then they apply some local computation, and then they send messages. This is the first round. Each party can send a message to one of the other parties. And this message, I said the channels are private, which means that if red speaks to yellow, then brown does not see this message. And this is a private channel. So we have a first round, and then again some local computation, and again a second round, and so on and so forth, till the end where the parties generate their output. And so this is a very natural model. And the main, the most important result is this. And this model is from 88 by PGW and CCD. This is it shows that basically you can compute every function as long as you have an honest majority. Okay, so as long as the adversary corrupts less than half of the parties, you can compute everything. And it's also shown that this result is optimal. So you cannot hope to achieve a larger threshold. Right? For some function, this will be impossible. Okay. So this is amazing, really an amazing result. What's the number of rounds? Or what's the smallest number of rounds that is possible to achieve? So someone wants to guess? Many silent students. You can if you're shy, you can just write it in the chat or something.
Actually, so the question is like actually we have a limited size Zoom room, so many students are in the broadcast channel, not in this room.
Ah, I see. Okay, but we have one. Okay, someone says 2. Excellent. So it's very easy to see that a single round does not suffice in this world, right? You cannot just, you can convince yourself easily that a single round cannot be secure, although you can solve the problem insecurely in a single round just by sending your input, right, to everyone, and then everyone can compute things locally. But if you want privacy, then you cannot even achieve one privacy in a single round. But it turns out, this is relatively recent result, we showed that 2 rounds suffices. Right, so this is with Brakerski and Tsabary, and concurrently Yuval Ishai and Srivanathan also showed a similar result. So 2 rounds suffice. That's great. I mean, I said that you cannot hope for anything better, but actually you can. So I should mention there are some extensions to active adversaries. This is with the current co-authors. And depending on when you move to the active setting, it's more tricky to define security, and there are different variants, and accordingly you can get different results, either 2, 3, or 4 rounds, depending on how greedy you are with respect to active security. Anyway, so let's stick to this passive setting, and I said 2 rounds is the best that we can hope for, but actually you can hope for something slightly better. So consider this client-server model. This is from Barkol et al., where you have clients with inputs and servers that have no input. And you have a very simple interaction pattern, right? I mean, each client sends a private message to each of the servers. The server applies some local computation, and then they send it back to the clients, and then the client should be able to output the result. So you can think about this as a distributed variant of fully homomorphic encryption, right? In the case of fully homomorphic encryption, you have a single server. So it turns out that the previous result from the previous slide extend to this model, as long as you assume that you have honest majority among the clients and among the servers. So you need honest majority here and here. That's nice, but actually, if you look at the original Barkol et al. Paper, they asked, can you get privacy when you have honest majority among the servers, but arbitrary corruption over the clients? And you can see that from a practical point of view, this is really motivated, right? Because clients are easy. Someone can do what people call Sybil attacks, right? They can generate many dummy clients, the adversary, and this way maybe corrupt many of the clients. Servers are hard to corrupt. Maybe I have even, 3 servers like, I don't know, Yahoo, Google, and Microsoft, and I trust that the majority of them are honest, or, 3 agencies from the government or whatever. Right. So there are few servers, and it's more natural to assume honest majority over the servers than assuming honest majority over the clients. So what's known about this question? So almost nothing, right? This is a very basic question. Even think about the 3 servers case. Almost nothing is known, right? It's open. It was open even for 3 clients and 3 servers. And even if you relax security and allow yourself to use computational security, the only known solution that we have is based on a non-black box use of oblivious transfer. Okay. So this appears in this paper. It's strongly based on the paper of Garg and Srivanasan. So really, the situation is, if you want to kind of apply such a protocol in practice, we have no solutions. So this is our first problem. Can you kind of interpolate between the first possibility result here, then this open question? That is, can you get a client-server protocol with honest majority of servers and up to T clients, where it is somewhere larger than n over 2 in this model? So this is the first question that we're going to ask. Let's move to this OT hybrid model. So here the parties are connected via point-to-point OT channels. So what are OT channels? So we have this magic box, which is connected to 2 parties, say Alice and Bob. Alice sends a pair of messages, can be bits or maybe strings, doesn't really matter, M0 and M1, and Bob sends a selection bit. Now Bob should receive the message that is indexed by this bit. So if Bob sent 0, then he should get M0. If Bob sends 1, he should get M1. Crucially, Bob does not learn the other message, right? And Alice learns nothing. Namely, Alice does not learn what is the selected bit. Okay. So this is oblivious transfer. It was presented by Rabin and later by Evan et al. Good. So in this model, each pair of parties is connected by these OT channels, and we have them like in a symmetric way, both when the first party is the sender and the other party is the receiver, and vice versa. And the protocol proceeds as follows. So we start with our inputs. We apply some local computation and send values through these OT channels. This is the first round. Then again, apply some local computation, do a second round, and so on and so forth until we generate the output. So this is the OT hybrid model. And here the most important result is first due to Yao and then in GMW, shows that you can get a perfect protocol for every function with full privacy threshold. So T can be as large as N. Right, again, amazing result. Yao proved it for 2 parties and GMW extended it to the multi-party setting. So kind of qualitatively it shows that OT, this primitive, is complete for multi-party secure computation. So it suffices to kind of realize this 2-party box in order to get a general multi-party secure computation, which is, interesting and super useful. Again, many real-world protocols use this paradigm. Again, we can ask, what is the number of rounds, right? I mean, how many rounds we need here? So guesses? Okay. So we know that we have one brave person who knows how to guess. So what's your guess now? Okay, perhaps circuit size. Definitely the circuit depth suffices, or even the multiplicative depth, but maybe we can do better. So let's see. So Yar's remarkable theorem, which is also known as the garbage circuit protocol, shows essentially that if you have only two parties, okay, so if we had only red and yellow, you could have a single round of OTs. It's parallel calls to OTs. So this is amazing. So we can say OT is non-interactively complete for two-party computation. Unfortunately, we know that this does not hold for more than two parties. So we showed a year ago or 2 years ago that this cannot be done even when n is larger than 3. So OT is not non-interactively complete in this setting. In fact, this theorem is kind of robust. So it holds even if you replace this OT box, this ideal channel, by a two-round OT protocol, which is a more liberal notion of object. And even if you replace these OT boxes by general two-party boxes, you know, more fancy functionality, as long as it's a two-party functionality, you cannot hope to achieve it with a single round. So what can we hope for? Well, we can do one of two things. Either replace this OT by something fancier and insist on the non-interactive reduction, or maybe allow slightly more interaction, right? These are the two natural approaches that we can have. So this brings us to the next two questions. So here's the first option. Can we replace this OT by some three-party functionality, right? So this is a three-party box. It connects to three parties, and it also gives, say, output to three parties. And the question is, can we achieve such a protocol, right, with a single round? And in fact, we can be even more greedy and ask for a simpler box where, you know, this is it's labeled by 3PC, but actually only two parties send their inputs to the box, and the third party gets the output. Okay, this is kind of the best that one can hope for. I should say that in this paper that I mentioned, we show that if you have a four-party box, then you can do it. Okay, so really the question is about three parties. An orthogonal line of research can ask, well, let's insist on OT, but try to minimize the round complexity. So can we derive a protocol of the form that we have a single round of OTs and then, you know, a round of plain model communication? And you can relax this question a little bit and ask, can we derive a three-round protocol given only a two-round ideal OT? So when I say this thing, I'm kind of counting a call to OT as two rounds because, you know, in any realization of OT, you're going to have two rounds, right? One for sending and the other one for the receiving. So think about even a physical realization of OT is going to take two rounds.
Okay, but this is a bit strange, right? So because OT, you can use OT as channel. So then the first round of OT, it's essentially the same as can be downgraded to sending a private message.
I'm not sure that I understand.
I mean, the first round of OT interaction, it can be downgraded. As a special case, you can use OT to just send a message, right?
Yes, of course. No, but I'm saying the following. You could allow two rounds of OT. I could put here a layer of OTs and here another layer of OTs. Okay, but this is I claim that this is a very weak or much weaker than the current picture. Why? Because in real world, say that I'm going to place some physical realization, say for some hardware realization of OT, then I'm going to wait two rounds, right, for each call of OT. One for, you know, plugging in the inputs and then for getting out the outputs, which means that if I have two levels of OT, I will get four-round protocol. So that's why I insist either on this picture or on a three-round protocol where you are given two-round ideal OT. So each call to ideal OT is counted as two.
Okay. I guess I get it. Okay, because I was thinking you are talking about two-round plain model. It's already sufficient for computing functions.
No. Yes. I mean,
but
not in the plain
I guess
model.
Here you mean there's no honest majority.
Yes, of course.
Okay, sorry.
we have no honest majority, and more generally, I can think about a circuit here or a protocol here where the depth of OT is at most 1. Okay, this is kind of a generalization of this model, and this is also fine. Okay.
Yeah, gotcha.
Good. So I should say that the partial solution to this problem was given by Patra and Ishai. They show that you can get a 3-round protocol in a computational setting, but given a black box access to a 2-round OT protocol, not a channel. And this is very different because, for example, in a protocol, you can kind of send the first messages and then say abort the second message, right? I mean, not stop the protocol, stop the execution. Such manipulation cannot be done when you have an OT channel, right? I mean, once you push in the input, that's it, right? The output is going out. So there are all sorts of things that you can do when you have an OT protocol and you cannot do when you have an OT channel. This is kind of a nitty-gritty discussion, so if it was too complicated, just ignore it. So all these questions are open for any t which is larger than n over 2, right? I mean, so that answers your question, Kiran, right? I mean, if we are below the n over 2, then these things are trivial. Trivially realized by the previous slides, but we are interested in the case where we don't have honest majority. Good. One final question before we get to the actual results. So let's forget about round complexity and still stick in the OT hybrid model. So we have many rounds, but now we want active security. So it turns out that you can get active security even with a full threshold, but you get statistical error. And you get you get both negligible correctness error and negligible privacy error. And we know that you cannot hope to get perfect in both of these. You cannot reduce both errors to 0 unless some unplausible things happen. So the question is, can you get perfect privacy against an active adversary and forget about correctness? Maybe correctness, let's just settle on correctness which is imperfect even for a passive adversary, right? So can you get the highest level of privacy and with some non-trivial level of correctness? Again, this is a very basic question, and it's open basically for any t larger than n over 2. Even for t which is say n over 2 or beyond n over 3, this is a non-trivial question, but I believe that it can be solved affirmatively. Okay. So this is our 5th question. So let's talk about today's model, this 2-MPRE. So our model is very simple, right? I mean, we have our parties. They are allowed to do some local computation, and then they can throw in their inputs to this box, which is restricted to compute a degree 2 function. Okay, and that's it. Right? They get the outputs, they do some local computation, and they should generate the output. So that's the model. This is the 2-MPRE model, basically. It was defined differently, but that's the essence of the model. And you can think about it if you want to compare it to previous model as a relaxation of the parallel calls to OT. Why? Each OT you can verify it's the degree 2 function. So this is a stronger version of this model in the sense that here we have a degree 2 function which is decomposable to 2 parties. Right? In particular, if we had a solution in this world, then it would imply a solution in this world. Of course, this implication is not very useful because we said that, for values larger than n over 2, this is impossible to achieve. But just to give us context. How does it compare to this BGW model, to the plain model? Well, if you have a solution in this world, then you can replace this degree 2 functionality by a 2-round protocol, as Kenren noticed a few slides ago, and then you can get a 2-round solution for this world. And indeed, this theorem that I stated before was proved exactly this way. So we came up with a n over 2 private solution for this world, and then compile it to this world by just replacing the degree 2 functionality. So that was the original motivation for studying this creature. And let me mention another point about this proof. The way that we proved it, the construction was actually based on a protocol, but with many rounds. And we showed that you can take a multi-round protocol in the plain model and transform it into a degree 2 this 2 MPRE framework. And I should say that there are other constructions of 2 MPREs, one of them by Trenren, but actually they all implicitly rely on these plain model protocols. So they're all restricted to dishonest majority setting. So the question, this is going to be our main question, can we construct these protocols beyond honest majority? So non-construction are based on this plain model, which is inherently honest majority model, but maybe if you look at this in fresh eyes, you can go beyond n/2. Okay, so this is our main question. And as you will see in a few slides, this question turns to be closely related to all the previous questions that I asked. So our main result is a construction of this 2 MPRE that achieves privacy, and, which is beyond dishonest majority threshold. It goes up to 2/3. Okay, so this is the main theorem. And we can actually show that any tiny improvement, if you can push it to ceiling, for example, or to 2/3 plus epsilon, then you can go up all the way to n. So I don't know whether this is possible or not, but if you want to get full security, it seems that you don't have to work that hard. Or maybe this is a natural barrier for stopping, I don't know. As a corollary, we get full privacy for 3 parties, right? Because we can overcome a coalition of 2 parties, and a coalition of 3 parties is trivial in this case because they have all the inputs, so there's nothing to simulate. We also get equivalence theorem between this notion of 2 MPRE and many other models. So let me show you this theorem. So remember that we talked about single round protocols from 3-party primitive, and 3-round MPC from 2-round OT, and MPC from based on 1 round OT plus 1 round of plain model communication. So all these things are equivalent for every threshold T. Right, so this gives us new result in this domain for T which is larger than n/2 and smaller than 2/3. We also know, and this was also observed in a previous work, that 2 MPREs imply client-server protocols, and as a bonus, we get a full resolution of this problem for 3 clients and 3 servers. And finally, and this is probably the most surprising connection, we can prove an equivalence between this 2 MPRE problem and this the notion of perfect privacy under some weak version of active attacks. Okay, in the OTO model. So this is somewhat surprising, because here we kind of relate a passive primitive with low R complexity to a highly interactive primitive with active security. So this seems to be like 2 very different beasts, but there turns to be a very close connection. And I should say that this can be viewed as a new approach towards breaking these 2/3. Right? I mean, if you can kind of make progress in this world, then you can really solve this thing. Okay, so how much time do we have?
20 minutes.
20 minutes, perfect. So I'm going to tell you a little bit about this construction, then a little bit about this interesting direction from active security to MPRE, and then we'll conclude. Okay, so we want to construct 2 MPREs for 2/3 that are resilient to 2/3 adversary. So this is the model. Remember, local computation, degree 2 functionality, and then local computation. So we are going to do it in 2 steps. In the first step, I'm going to show you that if you have a protocol where you have plain model communication, and then at the last round, a degree 2 functionality, then you can compile it to collapse all these rounds and get this kind of protocol, right? I mean, you can collapse all these plain communication rounds and kind of push them into this degree 2 functionality. So this is the round collapsing lemma. And in the second round, I'm going to design a protocol in this world, which is going to be a much easier task for this threshold, and then compile it using the first step to this 2 MPRE model. Okay, so let's start with the second step. So, in fact, I'm going to use just a single round of plain communication. And by known results, it suffices to focus on a degree 3 functionality, and for simplicity, let me think about this simpler functionality where 3 parties, 1 party holds X, 1 party holds Y, the third party holds Z, and the fourth party should learn X, Y, Z. So we have 4 parties, and the corruption bound is 2. Note that this is beyond honest majority, right? Honest majority is less than 2, which means that you're allowed just 1 corruption. Okay, so this is what we want to achieve. X, Y, and Z are the inputs. We're going to have single round of communication, then some local computation, and then a call to a degree 2 functionality, and at the end, this green party should learn X, Y, Z. So the protocol is actually quite simple. Let's see. So, as usual in this protocol, you start by secret sharing. So let's do secret sharing. So the red party has its input X. And let me break it to 6 random pieces such that their sum is going to be X. And this is 6 random pieces. And the reason that I'm taking 6 is that I'm going to allocate a share for each pair of parties. You see that these shares are indexed by sets of size 2. And the reason that I'm looking at sets of size 2 is because this threshold T, right? So I want to be secure against any coalition of size 2. So I'm going to allocate for each coalition of size 2 a share. Okay. So I'm going to break X to these 6 random shares. This is known as CNF sharing. And then the red is going to distribute the shares. So how is red going to distribute the shares? So let's see. What does the red send to the second party? Well, we have 6 shares, but we're not going to send all of them. We're going to send all the shares in which the name of the party, 2, does not appear. So if 2 appears in this coalition, I'm not going to give him the share. So only 3 shares. Right? X13, X14, and X34. Similarly, I'm going to give the brown some shares and the green some shares, and for symmetry, I'm going to give myself also shares. I mean, why not? So let's look at the privacy so far. So I claim that every coalition of 2 parties is missing a share. Right? So let's look at green and brown. Okay. I mean, if you look at all their joint view, they have they have 5 different shares, but they don't know the share X3, 4. Right? Because this is the share that corresponds to this pair, right, by design. Right, 3, 3, and 4. So far, this protocol is secure, right, against pairs of parties. Good. Now, what am I going to do? Well, I'm going to do the same thing for the second party, same thing for the third party, and the fourth party has no input, so I don't have to take care of it. Now remember that my goal is to compute this product XYZ. And X can be written as the sum of all the shares, and similarly for Y, similarly for Z. And therefore, by opening the parentheses, I get many degree 3 monomials. Right? And I claim that each of these monomials is covered by 2 parties. I mean, why? Let's look at this monomial. So this monomial, for example, is covered by the red party, right, who holds X2, 3, and the Y3, 4, and by the brown party who holds the Z1, 2. In fact, this monomial is also being covered by the yellow and green, right? There are other ways to cover this monomial. And why does it hold in general, right? How can I prove that each monomial is covered by 2 parties? Well, each variable, right, each share is held by 2 parties, right? Which means that if I had an uncovered degree 3 monomial, then the number of parties would be 2 times 3, right? I mean, I would have 2 times 3 disjoint parties, but I have, which is 6, but I have only 4 parties. So this is a contradiction. Good. So I convinced you that each monomial can be covered by 2 parties. So what are we going to do now? So we are going to locally generate all the possible quadratic terms that we can. So each party is going to compute all the quadratic terms. Particularly, we're going to have this quadratic term here, and this degree 1 expression here. And now we can call a degree 2 functionality to generate this sum. Why? Because after this pre-processing, I just say generating this monomial is just a product, a degree 2 function of these 2 variables. Right? This is kind of a new intermediate variable. And we are done. Okay, very, very simple, and you can easily generalize this thing to larger values of n and t. So if you do the naive generalization, then you will get a security threshold of 2/3 minus 1, and by using an additional trick, you can get this 2/3 threshold. Good. So let's try to collapse rounds. So we have a multi-round protocol, and we want to collapse many rounds. So let's start by just a single round, and then use induction to collapse more rounds. Okay, so let's assume that I have one round of plain model communication plus a degree 2 functionality. And in fact, let me make my life even easier and assume that this degree 2 functionality is decomposable to 2 blocks. So what does it mean? So instead of having a general degree 2 functionality, I have this TOT. This is a 3-party version of OT. So what does it mean? Let me define it in a minute. So it means that Alice and Bob send some input, and the third party gets the output. Right? Forget about the actual. The definition says that Alice has a capital A and the lowercase a, and the B the same, and the output that goes to C is the product of the capital A and B plus the sum of the lowercase a and B. This is, and we can show, I'm not going to show it here, but we can show that this degree 2 functionality can be compiled into TOTs. So it's not that trivial, but it can be done. And let me further restrict my attention to a single path in the computation. So let's look at this part of the computation. Okay. So I want to collapse this round. Okay. So let me even more trivialize the problem up to the level where it's really trivial. Let's assume that brown and green do not communicate with red and yellow. So if this is the case, right, the red edges are being removed, then the problem is really simple. Why is it simple? So I'm not going to wait to your answers, but let me answer. So because this is just a 2-party computation with a receiver. Right. So, you can basically, or at least intuitively, you could use a generalization of Yao to replace all this thing by a single round of parallel calls to TOT. And indeed, this intuition is correct. Let me show you the proof in a second. And this will be useful for the more interesting version where we have some of these edges. So let's go over the proof. So we want to compute a function of x and y. So I can write it as a polynomial, right? Where in each monomial I'm going to have 2 colors, right? I mean, 2 variables that are colored red and variables that are colored blue. And I can, by doing some local pre-processing, I can replace it by some capital X and capital Y, right? These are some local variables that are computed by the red party, and this is by the yellow party, whose inputs are blue because blue fonts are bad for reading. Good. So now I'm going to randomize this sum by using a well-known trick. So what's the trick? I'm going to encrypt each monomial here by some random key. Okay, so this is another monomial, etc. So each of these monomials is being encrypted by some random key. Where are the keys coming from? Let's ignore this point for a second. These keys are being selected by by some ideal hidden entity. Now, I want to allow you, so far if you look at this thing, you learn nothing about the value of this product, also nothing about x and y. Of course, I want to release the sum, so I'm going to release the sum of the keys. And you can convince yourself that given this information, this is called randomized encoding, given this information, you can really recover the sum just by summing up all the first entities and then subtracting the sum of the keys. And you learn nothing else. That's very important. You learn nothing about each of the individual monomial. Now, how to select these keys? Well, I'm going to let Alice and Bob jointly select the keys. So each of these keys is going to be the sum of keys that are selected by Alice and Bob. And again, this is crucial. We must let both parties to participate in this selection, because if I let this, say, Alice choose this key alone, then Bob can learn this. Then Alice, when she sees this, she can learn the value, say, of y1. Right? She can learn this monomial, and she know x1. Say that x1 is 1. She can learn the value of y1. So I have to select the paths jointly by Alice and Bob. Good. And if you plug this thing in, you will see that we get this expression. This is just many parallel calls to these TOTs, right? Each of these calls. Good. But this was, as I said, this was trivial. So let's add an edge, a single edge. How much time do we have, Tina?
Let's see. 10 minutes, I guess.
10 minutes. Good. So let's add this edge. So the problem is that now we are going to have like 3 colored monomials, right, of this form. So this R is going to be the sum of all the R's, but let's ignore it. I mean, we don't care about additive terms here. So, okay, so we have 3 colored monomials. And the crucial observation is that the red party knows this value. This is capital Z. This is not a small z. This is the Z that the brown sent to red, right, in this, over this edge. So the red party knows both X and Z. So if this party knew it ahead of time, and before the protocol would start, then he could preprocess, right? He could kind of compute the product. But he cannot preprocess because he doesn't know it ahead of time. He knows it only on this point. But we can still save the day by letting, by exploiting this fact and letting Alice, the red party, to randomize the Z part alone. So what do I mean by this? Let's see. So the red party is going to sample a random A. And let's put on the table a description. We're going to communicate a description of Z plus A. Okay. So this is an encryption of Z under the key A. In addition, I'm going to encrypt the other part of this product, right? I mean, the XY part. And here I'm going to use, you see a black R. This is going to be, say, the sum of the randomizer of Alice and Bob, or maybe even Alice, Bob, and Charlie, right? Everyone. Okay, so black variable 0 correspond to sum of 3 colored randomizers. So I have an encryption of Z. I have an encryption of this thing. I showed you in the previous slide how to compute the sum of this thing by listing the sum of the keys. But now I want to compute the product of this thing. So luckily there is a known trick for this. So this term is kind of confusing at the first time you see it. Let me explain. So I can, once I give you the encryptions here, I can kind of multiply the ciphertext. So if you multiply the ciphertext, you get the product of this thing with this thing, which is the thing that I want. But also I will get this product of this thing, and this, like 3 other products, which are not interesting. So this is kind of the key that I'm going to give you. I'm going to give you these 3 uninteresting products, minus the randomizer that was here. And now you can show, again, you can convince yourself that on one hand, by multiplying these 2 entries and adding this 3rd entry, you will get this value. Just open the parentheses and see. And on the other hand, the information that is going to leak by this triplet is not going to be more than the information that was here. Now, note that I did here something which is typically prohibited, right? I encrypted Z under a key which was owned by Alice. Typically, I want to encrypt things by keys that are shared by all the parties. The crucial observation is that Alice already knows Z, and therefore, it's okay to let Alice encrypt it. And now the magic happens, right? I mean, each monomial, so all these things are degree 2. And in this thing, I have degree 3 variables, but the degree 3 monomials are only 2 colored, right? Which is great because now I can just replace this thing by a degree 2 function, right? After local preprocessing, I can compute it by a degree 2 function. So that's how I do the round collapsing. Good. Now you have to work harder when you have more parties connected here because you're not going to get naturally degree 3 things, but there are ways to kind of transform the computation to a degree 3 computation, and that's what we use in the general-MPC. Okay, so I have like a few minutes to talk about the active to security to MPRE thing, so let me do it fast. So we have, our goal is to take this multi-round protocol with perfect active privacy and compile it into this 2 MPRE. So let me start with a an easier task. Sorry, the animation here is kind of bad. So ignore this. Ignore this bullets for a second. So I have a plain model protocol. I want to kind of transform it into this model. Let me show you a new transformation. So let's call this protocol pi. So the idea is that each party is going to try to sample locally a complete view under pi. So what does it mean? So each party is going to sample random incoming messages for all the protocol. So I'm party I, so I'm going to say to sample all the incoming messages for each other party for each round. And then, conditioned on these incoming messages, I'm going to compute all my outgoing messages. And now in this box, I'm going to do the following thing. I'm going to send all these things to this box. And this box is going to do the following thing. Then to check whether the messages are pairwise consistent, namely incoming messages equal to outgoing messages. And if so, it's going to check whether the final output is indeed 1. So I'm going to send this box also my final output of the protocol. And it's going to output 1 if this is the case, otherwise it's going to output 0. So let's analyze the correctness of this box. So I'm going to get a consistent transcript with probability 2 to the minus c, where c is the communication, right? The number of bits that are exchanged in this protocol. So this means that I'm going to have a huge error of 1 minus 2 to the minus c. Remember, everything here is finite, so these are constant eventually. And I can reduce it by using repetition. Of course, in order to maintain privacy, I will have to argue that I have perfect privacy. Otherwise, I'm going to lose in privacy when I do the repetition. So let's analyze the privacy. So I claim that I have perfect privacy here. And the intuition is that, well, what the party gets here is either a 0 value or a valid transcript. And this can be translated into a formal proof. Now let's look at this box more closely. What are we computing here? We're computing here end of many equalities. Right? We check equalities between pairs of messages. And this is a very nice predicate, right? End over equalities. In particular, we can kind of use a well-known trick and replace end with random inner product. So let me explain. We're going to replace it by this expression. And the trick is that, if all the equalities are indeed 1, so these things are always 0, then the outcome is going to be 0 here. Right? And on the other hand, if at least one of them is non-equal, then I'm going to get here a uniform value. And think that I'm working over a large field, this does not implique more information, and it increases the error by, say, 1 over the field set. Okay, so I'm seeing Uri here, so I have like 2 more minutes, or do I have to finish? How are we doing with the time?
Well, I guess
5?
in 5 minutes at most. Yeah.
5, okay, 5 is more than I need. I will. So this R as usual is going to take to be used as the sum of all the randomness of the parties, right? It's very crucial. Otherwise, I'm going to leak information on individual pairs of messages, but still this is going to be a degree 2 thing. Excellent. So we get a new very clean reduction to a degree 2 functionality. But we really care about this OT model, right? I mean, that was the point. So we can do basically the same idea, right? I mean, ask each party to kind of guess the incoming messages, now also the incoming OT messages, and send everything to this box who tries to check whether things are consistent. Okay. So now, instead of checking equality, we're going to check whether this 4 tuple is the consistent OT tuple. Okay. But now we have a problem. Because this equation is a degree 2 equation, and when you multiply it by the R, you get a degree 3 equation. So this is bad. So we don't know how to solve this problem. The only solution that we have is to let this randomizer, this specific randomizer, be chosen only by the red and the blue party. So if this is the case, then the whole thing here, this whole expression can be turned into a degree 2 thing. Because it involves only 2 parties. But now we leak information, right? Basically, these red and blue parties, even if their OT is inconsistent, they know this expression, and therefore they can check whether the rest of the transcript is consistent or not. So this is a leakage of information, and this is in general non-private, but we can show that this leakage of information can be translated into an active attack in this world. So if we had perfect active privacy in this world, then we could get a perfect privacy. So that's how we cope with it. And indeed, in fact, by looking closely at the type of corruption that we get here, we can actually define a notion of weak active adversary and show an equivalence between these two worlds. Okay, so if we define this notion, and I don't have time to define it, so let's skip it. Good, so let me conclude. So we talked about the play model, we talked about the 2-MPRE model, the OT hybrid model. Look at the threshold. Here we have honest majority, here we have 2/3, here we have up to n. So intuitively, this model is somewhere between these two models. And indeed, there is a well-known result of Beaver that shows that the OT hybrid model is equivalent to this model, where we have a degree 2 function and then plane model communication. And I showed you that the 2-MPRE model is equivalent to a model where we have plane model communication and then a degree 2 functionality. So it's very clear that this model is more liberal than this model, right? Everything that you can do here, you can do here. Whether this model is as powerful as this model, this is an interesting question. And indeed, this can be like, this is essentially the question of increasing the threshold to n. Right? So if you can show that, you can compile a protocol that starts with degree 2 to a protocol that ends with degree 2, then you can prove this full threshold. Good. So let me just remind you this picture here, and mention that this is an intriguing connection, as I already said. And one final comment. We show along the way that n over equality is complete for honest majority MPC. And this may be, this seems to be like a useful observation, and we're kind of wonder what are the applications for this. For example, I don't have time, but I could describe you a nice physical model for MPC where parties have pipes and send liquids over the pipes and so on, that allows them to securely compute the function. So it will be nice to further explore this direction. So thank you very much, and I'll be happy to take questions, although I think the tour is already ready to start.